Here we are, the last lesson in this unit on one variable statistics. And we are looking at
measures of relative position. Now this is sort of a subset of measures of dispersion. Remember that measures of central tendency are looking at the center value, the mean, median, or the value that's repeated most, the mode. Measures of dispersion that we've been looking at, like variance and standard deviation, look at how each point is in relation to the mean. Okay, so we're comparing ourselves to the mean always. But now we're going to look at measures of relative position where instead of comparing ourselves to the mean, or instead of describing the mean or the middle value, we're going to take a data point and we're going to compare it to other data points around it. Specifically, we'll compare it to all the data points that are below it, that are at or below it. Okay?
Okay. So really, you know, we've looked at the standard deviation in populations, the standard deviation in samples. We've looked at raw data. We've looked at group data. And that's what's come. Now we're going to add this final piece, which is relative position. And the first place, the place where we're going to start, because we're going to describe a couple of these, but the place that we're going to start is with quartiles and the interquartile range. So quartiles, of which there are 3, divide a set of data into 4 groups with an equal number of values. So it's similar into how the median divides data into 2 groups with an equal number of values. Quartiles divide data into 4 groups. The interquartile range is the range of the middle half of the data. So it has a value that's Q3 minus Q1, which is the third quartile minus the first quartile. With a larger interquartile range, you have a larger spread of data.
And the thing to note here is that because the interquartile range doesn't use the lowest and the highest, so remember how normal ranges take the highest datum minus the lowest datum, and then that's your range, but you fall victim to outliers when you only use the 2 extreme points, where the interquartile range, if you're comparing interquartile ranges for different samples or different populations, then the interquartile ranges, it can be compared more easily because we've lost any outliers, if there are any. So it's a nice way to compare data without falling victim to the outliers, messing up your mojo.
That's great. So a box and whisker plot is, or you know, conversely, a modified box and whisker plot are illustrations that we can use to demonstrate quartiles and interquartile ranges. So the difference between a box and whisker and a modified box and whisker is that the latter shows outliers. Okay? So a modified box and whisker plot will show outliers where a regular version will not. Okay? We have a test to determine whether a point is outside of our data range. And we're going to discuss these 2 conditions here and here. We're going to discuss them later. But this is a test that we can use to determine if something is an outlier. And it's basically, if it's beyond a certain range, then we say it is. So we're going to come back to these 2 little formulas
in a moment. We'll do an example,
But here is a typical example of a box and whisker plot. Okay. What we will notice is that we notice upper and lower data points, right? So here and here. And we notice this box in the middle. Okay, so this is known as the box. These are, of course, the whiskers. This end of the box right here, our leftmost end, is the first quartile. Okay, so the whiskers run from the lowest datum to the highest datum. This end of the box represents our first quartile. This end of the box represents our third quartile. And a line that's drawn somewhere within the box represents our median. And what's important is that this horizontal line that extends from the lowest datum to the highest datum is like an axis. And it must be scaled just like you would scale an axis. Right? It doesn't necessarily have to start at 0. It doesn't have to start, but it must be scaled accurately and consistently so that we get a good range for where these values lie.
And the picture is interesting because it can show you density. Bearing in mind that quartiles break the data up into 4 equal-sized groups based on the numbers of data. So, you know, 10 data points here, 10 data points here, 10 data points here, 10 data points here. if you had 40 data points.
Exactly.
And but note that where the median is, that the median to Q3, there's not a lot of distance, but there's still going to be the same number of points in that tiny little spot as there are in the space between Q1 and M. So it also helps if you picture them as being the same number of points, in between each of these lines, that there's a greater density that's packed into a smaller range between the median and Q3. So visually it does give you a lot of good information.
Yeah.
Yeah.
Here's a modified box and whisker plot. Basically almost identical, except now we have, ta-da, 2 outliers.
Yeah.
Okay? These outliers can occur above the highest datum. We could also have them below the lowest datum.
Yeah.
They could be on either side. You could have a low outlier and you could have a high
Yeah.
outlier.
And you can have more than one or just one or none.
Yes.
Right. But we'll show you how to calculate that when we do the example.
All right, so here we go. A random survey of 15 people walking into the school were asked how many times they've attended a live concert. So these were the results. So we had 3, we had 2, we had 1, we had 10, and so on and so forth. Determine the median, the first and the third quartiles, the interquartile range, and any outliers. Draw a modified box and whisker plot.
If necessary. Otherwise,
right.
just a box and whisker.
So
plot.
now we're dealing with medians here.
Yeah.
So we need to get these into an ordered list.
Yep.
So that's our first step, is to take the lowest to the highest, but have them all ordered in a row. So we've simply taken this data and we've transposed it, and we now have an ordered list.
Yeah, ascending order from lowest to highest. And so the first step is to find the median. And so we want to find the middlemost value. And since there are 15 data points, remember we talked about it, if it's an odd number of data points, your median will be one of the data points.
Yep.
So if you subtract 1, you get down to 14. So you know that there should be 7 data points on either side, so that your 8th data point in from the left will be the median. Okay, so let's mark that out. Now the median, which is the middlemost value, is 4 for this set of data. And we also want to find Q1 and Q3. So what we want you to think about is that Q1, which is the first quartile, is just the median of the lower half of the data. Okay, so it's the middlemost value of the lower half, which gets you a quarter of the way in. In order to find Q1, you have to exclude your actual median. So that point, that 4 that we picked, we can't use that. Let's draw a little bound around that, Mr. Jackson. We can't use that median to help us find Q1. So now we're going to exclude that, and we look at 0, 1, 1, 1, 2, 3, 3. Okay, and so there's 7 points in there. Again, that's an odd number. If I subtract 1 to 6 and divide by 2, that means there should be 3 data points on either side. So the 4th data point in will be our Q1. Okay, so that's the median of the lower half. Essentially, you're just going to find the median 3 times. Once for the whole data, once for the lower half of the data, and then once again for the upper half of the data. So again, we exclude the real median to find Q3. 7 data points, okay? So 4th one in from the top. And Q3 is the median of the upper half, so our Q3 is 8. So we've got Q1, the median is actually Q2, that's our 4, and then Q3 is 8. So we've got our bounds of our quartiles.
Now we say, okay, here's the box and whisker plot. So we've scaled out our axis, right? And we've developed our box around it. We've got Q1 that sits at 1. We've got Q3 that sits at 8. We've got the median, which sits at 4. Our lowest data point was 0, and our highest data point was 35. Here, we've replaced it with a dot to represent it was an outlier, and we've got our highest data point now set at 12. So the question you might be asking, this is an outlier, 35.
Let's measure the interquartile range. Yeah, let's measure the interquartile range first.
So here it is, Q3 minus Q1, which is of course 8 minus 1. So our interquartile range was 7. How do we know to label this as an outlier? We're going to use those couple tests.
Okay.
So basically, what we can say then is, all right, here it is. How did we know? How did we determine that it was an outlier? And so what we'd like now to do is to provide some kind of a meaningful representation of, okay, anything that's bigger than this is going to be an outlier.
Yeah, so we're going to use the interquartile range and Q1 and Q3.
Yeah, so really Q1 and then anything that's below 1.5 times the interquartile range, or Q3 and anything that's above 1.5 times the interquartile range is going to be considered an outlier. So let's look at the bottom bound, anything that's smaller. Q1 minus 1.5 times IQR would be 1 minus 1.5 times 7. And in this case, that gives us a value of minus 9.5.
That's not very many concerts.
No, in fact, this doesn't have
It's not meaningful,
a
yeah.
meaningful representation. So when it's something like this that actually starts at 0, we don't have to worry about a lower outlier.
Bound,
Yeah.
you know, because no points are below negative 9.5. It's not possible for the data we gathered. That means that at least on the lower end or the left end of our data, there's no outliers. So we can be confident starting at 0, which was our lowest value.
Now, if we look at the upper end of the data, which is where we think there might be an outlier, we say Q3 plus 1.5 of the interquartile range, which would be 4 plus 1.5 times 7. This I'm actually just realizing right now is an error.
That's it. It should be 8.
This should be 8
Yep.
plus 1.5 times 7.
Yep.
8 plus 10.5
Yep.
is actually 14.5.
Yeah, so that should be 18.5 there. So let's adjust that.
So we can do that right now.
We can fix that right now. Yep.
We are consummate professionals.
Look at this.
Fixing
Making
this.
mistakes and fixing them. Let's fix it right here too, Mr. Jackson.
Yep.
There we go. Yeah.
So basically anything,
Yeah.
this is the point though. Anything that's bigger than 18.5, i.e. 35, we have one outlier at the upper end of our data.
Yep.
So let's say we also had someone that said 20 concerts.
Yep.
That too would be an outlier, and we'd
an
have 2 outliers.
Yep. Yep. So this is a test to find outliers in the left end using Q1 minus 1.5 IQRs, and the right end, or the upper end, using Q3 plus 1.5 IQRs. This helps you figure out where are any outliers in your data, and then you can label them on your modified box and whisker plot.
All right, so now here we are. That's kind of quartiles, and that's really, I don't want to say that's all you have to know, because there's a lot packed in there, but that is the description of quartiles. That's how far we're going to go.
Breaks the data into 4 equal-sized parts.
Percentiles, on the other hand, break the data into 100 equal-size intervals.
Yeah.
Percentiles are a little bit more confusing. Quartiles seem to be more readily understood because very often we have more data points than simply 4.
Yes.
So it's easier to divide, a large number of data points into a small number of intervals.
Yeah.
It's more difficult to divide a small number of data points into a large number of intervals, if you know what I mean. Yeah. And very often percentiles will ask us to say, okay, you've got 40 items in a group divided into 100 intervals. That's a little bit more difficult to think about.
Yep. And often percentiles are most useful when you have lots of raw data, thousands or hundreds of thousands or millions, because then breaking them into 100 intervals is okay, right? Because you have so much data that you're working with. Of course, we don't want to give you 1,000 pieces of data and then work on that. So we're going to use an example where we only have 40 pieces of data, but then breaking 40 pieces of data into 100 intervals, it becomes a little bit of a mental challenge. But we'll show you. It's the same process whether you had 40 pieces or 400,000 pieces of data. We'll show you the method, and then it'll make sense.
All right. So percentiles are always labeled as P sub k, and as such, P sub k is an actual item of data, and it's called the kth percentile. So P90 is the 90th percentile. P72 is the 72nd percentile.
Yeah.
Okay. Yeah. In any particular set of data, K% of the data is less than or equal to PK.
Yeah.
So for P72, 72% of the data is less than or equal to the value of P72.
Yeah.
So it always lets you know, if you want to know what percentile you sit at, it lets you know what percentage of people are below you in score.
Yeah.
So if you scored, say, in the 98th percentile of the MCAT examinations, that would mean that 98% of people writing the MCAT for that year scored at or below your grade.
Yeah.
We always place the data in numerical order when working with percentiles. You just have to.
Just like quartiles or median, right? And same thing, lowest to highest.
Has to be in order.
Yeah.
So again, here's a little example down here that you can read through, but P80 means that 80% of the data is less than or equal to the value of P80. 20% is greater than.
Or equal. Now
Yes,
notice,
yes.
and this is where it gets interesting, that how can you have a data point where 80% is less than or equal and 20% is greater than or equal? It seems like that number shouldn't exist. And in fact, it will show you how to make that work. You do create a data value, especially when you have a small number of data points, where 80% are below and 20% are above.
Okay.
So we'll show you how to make that work.
So here we go. We're going to do an example right now where we have some scores for one section of Stat 101 at the University of Waterloo.
Yeah.
All right, so we've organized our data, starting here with our lowest data point 34 and snaking our way up all the way through to our highest data point, which is 99.
Okay.
Okay, and we want to say for these 40 scores, is it 40?
Yep.
Yeah, it's 4 times 10. 40 scores, let's find the 90th percentile. All right, so how do we do this? Well, the 90th percentile is the boundary between the lower 90% and the upper 10%.
It's the number where you say, okay, this is the number where 90% of the data is below it and 10% of the data is above it.
Okay.
Okay?
So how do I create that boundary? Well, first of all, we have to find the data point that represents
90% of the way in.
90% of the way in.
Yeah.
So we take 90% times 40 scores.
Yeah.
It's the 36th score.
Yep.
So if we go in order, we find our 36th score, which just happens to be 89.
Yeah.
Okay. It's between, though, the 36th and the 37th datum. Okay?
Yep.
So the 90th percentile is the boundary between the lower 90% and the upper 10%.
Right.
So here, with our 40 scores, this line right here represents the boundary because these are the lower 90% and these 4 scores are the upper
10%.
10%. So now we need to represent the boundary as basically the average between these two numbers.
Yep.
So what's halfway in between 89 and 91? P90 is equal to the average of those two, and it just so happens in this case that P90 is equal to 90%.
Yeah.
Now, we should point out that this is a coincidence.
Just a coincidence, yeah.
P90 does not have to be 90%. In fact, if this value had been 89, and this value had been perhaps
90 or
90
95,
or 95 or whatever,
yeah.
then this value would have been a little bit different.
Yeah.
So let's take another example,
Yep.
and you can walk through it.
Okay.
A certain student score of 75. Does that place the student at the 70th percentile?
Yeah. And now the reason percentiles are used this way is that especially if you're looking at admissions criteria, they want to take everyone at or above the 70th percentile or the 80th percentile. They don't want to take everybody who got over 80 on the exam or over 80 on the test
Because if that
could
test
be a
had
lot
been
of people.
easy,
Yeah.
had been maybe too easy for that year,
Yeah.
then all of a sudden now they've got way too many people.
Yeah. So this percentile ranking is often what they use instead of marks, like just everybody who got 75, they want to take everybody who's at or above the 70th percentile. So the way that we can figure this out, let's just find what value represents the 70th percentile first, and then we'll compare it to our hypothetical student who got 75. So remember, if you want to find the 70th percentile, you're finding the data point that's 70% of the way in from the left end. So if we do 0.7, so 70%, times n, which is 40, it's our number of data points, 70% of the way in to our 40 data points will be data point number 28. Now 28 is, that value and below is 70%, but we want to find the value where below it is 70 and above it is 30. So with 40 data points, we're going to take the 28th and we're going to add that to the 29th and divide by 2. So we're going to find the average. So here at 76, everything at or below 76 is the 70% of your data, and everything at or above 78 is the upper 30%. But we're going to create a data point here that doesn't exist, where we can say, here's a number where below it is 70% of the data and above it is 30% of the data. And again, the way we do that is we average those two values, the 28th and 29th data points, which in our case are 76 and 78. We add them, divide by 2 to get 77%. So that 77% represents the 70th percentile, so that a student's grade of 75% is below the 70th percentile. If they were trying to get into a program where they needed to have a minimum of being at the 70th percentile, they wouldn't have gotten in because they're below.
And even though they got a 75% in the course, they still didn't do better, or at least the same as 70%
of the students.
of the people.
Yeah.